It's a pleasure to resume this morning session with another speaker from Uppsala, Pietro Longhi, and he will be talking about the skein-valued mirror of topological vertex.
Yeah, okay, thank you, and thanks a lot for the invitation. So yeah, I'm going to tell you about a couple of works that came out last year with Tobias Ekholm and Lucas Nakamura, and Tobias Ekholm and Vivek Shinde. All these peoples are mathematicians, but these works are really about physics, and they're about the subject of topological strings. So let me very briefly remind you what is the topological A model. That's what these works are really about. So the topological A model is a topological quantum field theory that arises when you study world sheets that map from some Riemann surface into some target space. And as a topological theory, it actually localizes on holomorphic maps. Okay, so in fact, what we're going to need is, we don't even need X to be Calabi-Yau, we just need X to be some symplectic manifold. And what we're really interested in this set of works is the case where we consider not just closed world sheets, but open ones. And to have open world sheets, you need branes, which in the A models are called A-branes. And the basic data that defines an A-brane is two things. You want to have some Lagrangian submanifold. So that means that, you know, it's middle dimensional. So dimension L is half the dimension of X. And pullback of the symplectic form vanishes. But that's not all. You need a Lagrangian, and on that Lagrangian, you want to put some flat connection, which as a physicist, you can think of as some Chern-Simons QFT. So then the observables of this theory, what they do is they essentially count, in some suitable sense, holomorphic curves. Okay, and perhaps the chief example of such an observable would be something like the free energy. So the free energy takes the form of some polynomial in T and psi. So T for me would represent some closed string moduli, psi some open string moduli, schematically. So this polynomial contribution would come from constant maps. So these would be world sheets that map to points in the target space. And so as you integrate over the moduli space of these world sheets, what you compute is volumes, just volumes of the Calabi-Yau, or sorry, the target space or of the Lagrangian where the world sheets have to end. But then there's also some instanton corrections, sum over genus, number of boundary components, and relative homology classes with some coefficients, n, g, beta n, and then there's some e to the minus area, where the area is given by the closed string moduli, but also by some boundary contribution weighted by the open string moduli. And then all these are counted by powers of the string coupling to minus the Euler characteristic. So that's an example of an observable that you might want to compute. So this subject is, of course, very old. It's been around for, I don't know, almost 40 years. But it's a subject where there are some persistent challenges. There's still things to learn about it. And, well, some of the problems is that on the physics side, actual computations, just from the grounds up, are very hard to carry out. On the mathematical side, it's not so clear what it means to count holomorphic curves. There's no, well, at least as far as I understand, there's no well-defined notion of what people would like to call open Gromov-Witten theory. So there's no such theory that actually produces these numbers, as you would do in the closed Chroma-Witten case. But over the years, over the decades, there's been a lot of results, lots of progress. However, most of these, they go through some indirect routes. They either use things like large N duality or mirror symmetry, and you have lots of interesting results. But what usually happens when you go through some indirect routes is that you might miss some important facts about the theory. So that will be actually the main point of the talk. Let me make maybe the main point of the talk right here. So the main statement or the goal is to explain that a complete definition of the open string A model must include a certain piece of data that is never talked about in physics, and I will show you why it's so important. So it must include information about asymptotic data for Lagrangian A-branes. That's really the main point I want to make today. I'm going to explain what is this asymptotic data, why it's important, and what happens if you don't specify it. Now, it's not quite, just some fancy or abstract mathematical statement. We can compute what happens when you play with this asymptotic data, and it's actually relevant in many, many, many of the results that have been obtained through the decades, including some really important ones. So that's the one in the name of the talk, the topological vertex. So I will tell you that in many cases, in many results that have been obtained using large N dualities or mirror symmetry, well, actually, there's some implicit choice for what this asymptotic data is. It's just that it's not stated. In some cases, like in the case of the topological vertex, it's actually even implicitly stated, but then the result doesn't quite match with the geometry that's considered at the beginning. So there's definitely a bit of confusion. So let me just remind you, what is the topological vertex?
Very naive question. Asymptotic in what sense? In the sense you are considering non-compact Calabi-Yau?
Yes. The target space, I will give you like very explicit examples.
So if you consider compact Calabi-Yau, this data...
Yeah, well, then the whole story is much more complicated.
Much more.
Yes. In the compact case, there's, even in the closed string setting, there's some recent results by some groups, but I'm not going to say anything about compact today. Okay, so what is the topological vertex? I'm going to draw some picture here. Later I will explain what this means. This is supposed to represent C3 with three non-compact Lagrangians. We'll call them L1, L2, L3. And then the vertex is a formula. It's a rather nice formula. C lambda 1, lambda 2, lambda 3. So some partitions equal Q to the kappa of lambda 2 over 2 plus kappa of lambda 3 over 2, sure function of lambda 2 transpose in the principal specialization. You don't really need to know what these things mean. I'm just going to give you the formula. And then skew-sure functions, Q to the lambda 2 plus rho, and skew-sure function lambda 1 mod eta of Q to the lambda 2 transpose plus rho. So it's a strange looking formula. I'm not going to get into the details of what all these objects are. It's just a function of three partitions. And the statement that will be clarified later is that this combinatorial object should count for you all holomorphic curves that have boundaries on these three Lagrangians in C3. Okay? And this formula was derived in, I think, 2003 by Aganagic, Clem, Marinho, and Vafa. And it's one of the big kind of successes of topological string theory in the sense that you can do a lot with this formula. You can compute open and closed Gromov-Witten invariants in a lot of geometries. But actually, as I'm going to explain, what this formula really counts is not quite well stated or well understood. So we're going to clarify that. So it's definitely a very good formula. It's a correct formula, except that I think we need to qualify a little better what it actually does. So the first thing I'm going to do, the plan of the talk, is I'm going to tell you a little bit about what Rodolfo is asking, about what I mean by asymptotics of A-branes. I'm going to give you some details on that. Then I'm going to explain what the topological vertex actually counts. And optimistically, if time permits, I will tell you about actually a bigger picture that goes beyond curve counting. That is the subject of skein-valued recursion relations. And what this tells you about analytic continuation of curve counts, including of the topological vertex. So I'll try to explain what I mean by that when I get there, if I get there. It's related, yes. So, in the exponential network story, one usually deals with some M-theory construction on a Calabi-Yau threefold with some Lagrangian inside, and then you have a 3D, 5D system. If you place an M5 brane on that Lagrangian, here we're just looking at the topological sector of that. So you can think of passing from M-theory to type 2A, and then taking topological sector of type 2A, you get to the A model, and you're looking at that. So short answer is we're looking at the BPS sector of that setup. Yeah. Yes. Okay, so let me start by telling you what I mean by asymptotic of A-branes. And as I said, these are math works, but it's math with some interesting lessons for physics. So there's a framework in mathematics, which I'm going to briefly summarize, which is called the Legendrian contact homology. Sounds a bit scary, but you'll see that it's actually somewhat familiar. So what this is a framework that allows you to compute amplitudes just directly in the A model. So you don't need to use any dualities or mirror symmetry. It's not open Gromov-Witten theory. We're not looking at holomorphic curves in the bulk of the space. The point is that you're going to compute these amplitudes in a kind of holographic way. So we're going to do that from data at infinity. What do I mean by that? So what I mean is, I told you that we're interested in a situation where we have some symplectic manifold X with boundary, some Lagrangian inside, and now we look at the boundary of this system far away. In the far away region, there's a radial direction, R, times some boundary manifold that will be a contact manifold. So X will be, say, dimension 6, L is dimension 3, the contact manifold will be dimension 5, and the boundary of the Lagrangian will be some two-dimensional object called a Legendrian, just a name. It's a Legendrian submanifold of the contact boundary. Okay. So by data at infinity, I mean some geometric data of this pair here, of the contact manifold with the Legendrian inside. So I'm going to give you a very, very concrete example right now, because probably most of you have never really dealt with this kind of geometric structure. So let me give you an example that will be the main example of the talk, the one that we'll use throughout. So very simply, we take x to be C3. And in C3, we can take a Lagrangian parameterized as follows in coordinates Z1, Z2, Z3. I can give you an expression for L that goes as follows. So we take rho square plus R square to the 1/2 e to the I alpha, rho e to the I beta, rho e to the minus I alpha plus beta, where rho is in the non-negative reals. R is fixed, so R is just a constant, is a parameter, and alpha and beta are just valued in S1 times S1. Okay, so what is this Lagrangian? Well, topologically, this Lagrangian is just a solid torus, right? We have a torus parameterized by alpha and beta that shrink to a circle when rho is equal to 0. It's a circle in the first coordinate plane with radius r, and then it grows out. And so this is the data we want to study, and we want to look at what this looks like at infinity. So the boundary of S3 is, of course, just a 5-sphere, right? S3, C3 is R6, so the boundary is S5. And the Legendrian here is what happens when you take rho to infinity. But now you see you take rho to infinity, you get a torus parameterized by alpha and beta. Okay. So a picture of this boundary data goes roughly as follows. So you have your boundary manifold Y with some torus inside, which is lambda. And then in the interior, there is the radial direction in X. And then this lambda goes into our Lagrangian. So that's an example of this boundary data. Now, there's one point that's already important to make here and will be actually crucial for what I want to say later. I want to observe that I could have chosen another Lagrangian, right? Let me call this L1. I'm going to call L2 the same thing, where I take rho here and I take rho square plus R square to the 1/2 here and rho here, right? And the point I want to make is that if you look at the boundary of L1, is actually the same as the boundary of L2. When I take rho to infinity, there's no distinction between L1 and L2, okay? And if you're familiar with topological strings, or if you've ever seen diagrams like this, L1 would correspond to a Lagrangian here, L2 would correspond to a Lagrangian here, and you can place another one there. And really the main point is that at infinity, Li are all the same. They all go to the same lambda times r. Okay? They're completely degenerate. So when I tell you that we have a framework in mathematics that tells you how to compute amplitudes of the A model just from data at infinity, well, what that is telling you is that, therefore, what Legendrian contact homology will count is, or compute, is certainly not curves, is not counts of holomorphic curves, because such counts would be different for these three Lagrangians. But it's going to compute something a little bigger. It's going to compute, as we're going to see, it's going to compute some global information about counts of curves, not for a single Lagrangian, but for an entire family, for a family of Lagrangians with the same asymptotics. So in other words, so I'm going to tell you exactly what this framework does, but I just want to give you a heads up that we're not going to compute right away curve counts. What we're going to compute is something that knows simultaneously about these three different Lagrangians, okay? And then you can, of course, recover information for each of them individually. Same asymptotics. I mean that, so here's an explicit equation for one of these Lagrangians. I can give you L2 by just, as I said here, by swapping this radial factor with this one. And when I take rho to infinity, so I said this is a solid torus, right? So it looks like this, where there's some radial direction rho. And what I'm telling you is that when you embed this solid torus in C3, you have L1, you have L2, you have L3, but when you go to infinity, they all go to the same torus. You can see it from here, right? Yeah, the asymptotic series will come later, and that's the curve counts. These will be different. What I'm saying is that, I'm going to give you some framework that just takes this data at infinity. It will produce that asymptotic series. But the point is there will be different asymptotic series for L1, L2, L3. So what we're going to compute is not the asymptotic series, is some global structure that encodes all the possible asymptotic series. Okay, thanks. Yeah. We'll get to that now. Yeah. Yes, we'll sketch also the physics of this construction. That's why I want to go over it. It's not just math. So let me now get into the details a little bit more, and I hope it will make sense physically. So what is the data at infinity? At infinity, so of this pair of the contact manifold and the Legendrian times R. Well, most important thing is when you have a contact manifold, you have a vector field called the Rabe vector field. And so this is something related to the symplectic structure on X. So it's something that remembers about the symplectic structure in the bulk, except that it only lives here at the boundary. And why do we care about the Rabe vector field? Because, well, the complex structure on this manifold rotates the vector field along the radial direction into the Rabe vector field. So in other words, maybe better stated this way, is that holomorphic curves, like the well-sheet instantons that compute your free energy, that run to infinity must end along Rabe flow lines. So if you have a world sheet in this A model that runs all the way to infinity, then such a world sheet must have a boundary along the flow line of the Rabe vector field. So you could have curves like that, where the boundary is along flow lines of R. So that's the picture for a closed string world sheet, right? So it's a closed string with a puncture at infinity. But more important for us, you can also have flow lines with boundaries on the Legendrian. So there will be so-called Rabe chords. These are flow lines of that vector field between 2 points. So chord C has endpoints C plus C minus. And that flow line will be boundary for some open string, where the open string now has its world sheet ending on the Lagrangian everywhere inside. but then it has an open end along the Rabe chord. Okay, so that's why we care about these Rabe chords. Okay, so as you know, holomorphic curves are BPS in the sense they're minimal area world sheets. And likewise, the Rabe flow lines or the Rabe chords are in fact minima of the string action function. So that means that if I give you 2 points, C plus and C minus on my Legendre at infinity, I ask you what is the minimal length string that can connect those, it's actually the Rabe chord. And since they're minima of the string action, you can build a space of vacua, so the space of classical vacua for the string, as a vector space over Rabe chords. So you can build a vector space generated by Rabe chords where each of these states corresponds to possible ways that strings can end at infinity. What do I mean by string action? It's this thing. It's the area. It's this thing that before I called beta t minus. Yes. You have to take some scaling limit. Yeah, there's some. Yes. You can define this length as area divided by the length of the neck when you go to infinity. Yeah, there's some technical definition that's in the paper actually. So that's a good point. Okay. But now the point is that if these are the shortest paths that we can have at infinity, these are like what I call the classical vacua. And when I have a collection of Rabe chords, what I really mean is that I'm looking at some sector of my string theory where I have some chord Ci1, Ci2, Cin, and then I'm looking at all possible well sheets that kind of fill in this thing in the bulk, okay? And these boundaries of the well sheets will always be on our Lagrangians. Now, I call this the space of classical vacua because they're actually not stable vacua. They are destabilized by well sheet instantons, okay? And to describe how that works, well, mathematically, we have something called a DGA structure, which in physics is a little bit like a BRST kind of structure on the space of Rabe chords in the sense that we have some grading over the space of classical vacua. So we have some grading of this vector space by some non-negative integer. And, well, we have a product, which is this tensor product, which means we just take well sheets with more and more positive ends. And importantly, we have a differential. So differential will be some map that takes string vacua with degree r to string vacua with degree r minus 1. And it's a differential in the sense that it squares to 0. And the way that this is defined is very much like in Morse theory or Floer theory or any one of these familiar frameworks where essentially the differential acting on some collection of Rabe chords is going to be given by a sum over holomorphic well sheets with some weights. And then what it spits out is another collection of Rabe chords. So what that means is that you're going to have a differential that takes as an input some Rabe chords, as an output some possibly different number of Rabe chords. And what it does is it counts worldsheet instantons that map one vacuum to another vacuum. Okay? So this gives you some map from something that's in VR to VR minus 1. And the statement is that this can be defined with the appropriate weights and signs and so on so that it is nilpotent. Okay? So the idea is we have some classical vacua that are kind of very reasonable. They're the shortest strings that you can have at infinity, but then there's some destabilizing instanton effects computed by these differentials that tell you that the classical vacua are not the true quantum vacua. The true quantum vacua will instead be the cohomology of this differential. So the space of quantum vacua will be H star of V with respect to the differential. So I'm gonna give you some concrete example of that in a moment. Just one remark is that, as you can see, this whole construction, namely the presence of certain Rabe chords and the existence of certain holomorphic worldsheets that compute to the differential, it depends very sensitively on the geometry at infinity. You need to know how these branes, how these Lagrangians end at infinity. You need to know what is the geometry there. You need to have some control over what is this lambda and be able to, compute Rabe chords and holomorphic worldsheets and so on. And that's a data that is often neglected, but it's always there when you set up this kind of problem. And in some cases, it's not okay to neglect this data, as we're going to see. So I told you how this data at infinity defines this cohomology. So Chang-Yu was asking about asymptotic series. In other words, how do we use it? How to compute curve counts. So how do we get usual open string partition functions, in other words, from this data? So to do that, what we can do is the following. So we start on our lambda at infinity. Let's say we have some Rabe chord, C, and we're going to just choose a capping path. What I mean by a capping path is just we look at the endpoints of this Rabe chord and we choose any path on lambda that connects the endpoints. The reason for that is that once I have a capping path, then what I can do is I can look at some element A in the image of the differential. So that means that this will be some trivial element in my cohomology. And after capping, what this is going to be some collection of Wilson lines. I'm gonna give you a concrete example in a moment. But you see, the idea is that before capping, we just have these worldsheets, like this one, that have some boundary on L, except that they have some puncture at the Rabe chord. But after capping, we close it off, and we have a fully closed Wilson line on the torus at infinity. Okay? Now remember I told you at the beginning that the data that defines A-branes is not just a Lagrangian. There is a flat connection or a Chern-Simons theory there. So this will be Wilson lines in Chern-Simons theory on our Lagrangian. And by the usual axioms of topological quantum field theory, when you have a TQFT on a manifold with boundary, you have a Hilbert space of the Chern-Simons theory associated to that boundary. And if you have some Wilson lines on the boundary, they're going to give you an operator. So A will be some operator on that Hilbert space. Okay, so you get some operator on the Hilbert space of the Chern-Simons theory, and the fact that it's a trivial cohomology class should be interpreted as the statement that this operator must annihilate whatever state the Lagrangian itself defines. So again, TQFT axioms tell you there's a Hilbert space associated to the boundary, and there's a state in that Hilbert space associated to the free manifold itself. And what is Legendrian contact homology with bodies in the skein tells you is that when you build some trivial cohomology element like this, that is going to annihilate that state. So to make this a bit more familiar, you can choose a representation of this state as some kind of wave function. Okay, so that's what we usually call the open string partition function, usually with some variables x. So this is going to be some collection of variables. And then this reduces to the statement that we have an operator that annihilates the open string partition function. Okay, so that's what Legendrian contact homology really gives you. It's going to give you some operator that kills the open string partition function, except that, as I emphasized before, it can be any open string partition function for any choice of Lagrangian that, so for all L with the same Legendrian asymptotics. Okay, so the point is that once you have equations like this, there's unique solutions. And so that's the sense in which this structure really computes for you open string counts. So now I'm going to give an example concretely, finally. Oh, okay. Not too bad with time. Any questions about this? Yes? What is X here? X here is some notation to denote some representation of this state on some space of functions, right? So usually when you write down the open string partition function, you choose some open string moduli, what I called psi before. So xi could be some e to the psi I. So what I really mean here is that, let's say we look at some Lagrangian, and I can place a stack of n branes of this on this Lagrangian, right? So there's going to be many copies of the Lagrangian, and each of them has a position. So before, in fact, I gave you explicit expressions for these, and there was, this rho square plus r square to the 1/2 plus dot dot dot. So this r tells you about the distance of each of these from the vertex, and then this r is what would enter here. So xi is some open string moduli that tell you about the configuration of each of these branes. And there's going to be one for each brane in the stack. So if we're doing UN Chern-Simons, we're going to have n moduli. So this is, it's just some schematic notation to tell you that in the Chern-Simons theory, we really get some state in some vector space. Sometimes when we do topological strings, we like to pass to some representation of that over the space of functions. And that's what gives you these things that, for example, asymptotic series and so on.
But this is an operatorial equation, no? So
yes.
It's like different. You can represent it as a
exactly.
Exactly. And then you have to impose the asymptotic conditions, boundary conditions.
To exactly. That's exactly the point. Yes, thank you. So different solutions are characterized by initial conditions. So yes. So it's unique up to so that's when I say that this thing is some global statement about all Lagrangians with the same asymptotics. It doesn't really encode any curve counts per se, but when you want to count curves, you have to choose initial conditions, which means you go to some large volume region in the open string moduli space, right? Meaning that you take your branes far away on this leg, far away on this leg, and so on. And then you can make sense of curve counts. But it's all encoded by by this equation, by this operator that comes from data at infinity.
So it's a differential equation in the axis?
Yes, it's a differential or difference shift equation. Yeah. This, yeah. It's usually difference equations in this case. That's right. Okay, so let me give you one example. I'm kind of not even half of the talk, but going very slow. The,
Is this A some set of flow lines from Greek vector field, or what was the relation?
Yeah, so the A was, let's see, so I think I explained this before, but probably not very well. So when you have these rate flow lines, right, you look at the flow lines that have endpoints on the Legendrian. So these are going to be asymptotics for open strings that have boundaries on the Lagrangian and run to infinity. They must end on these flow lines. So then you have some vector space over those with some differential. So the differential counts worldsheets that start on some of these rate flow lines and end on some other flow lines. It's very much like in Morse theory, where you have some critical points. They're not the true vacua. They're kind of metastable vacua, and then you have some differential that counts things that flow from one critical point to another critical point below. And you have to compute the cohomology of that. Okay, so A is a trivial cohomology element. So this differential is something that counts worldsheets between the flow lines, between the rate flow lines, and A is a trivial cohomology element. Yes. Yeah, it's the same differential. Yeah. No. Yep. Right. So very, very briefly, just a simple example picking up from before. We were talking about C3 with this Lagrangian that was S1 times D2, the toric Lagrangian, and the boundary was S5 with a Legendrian torus. That's the boundary of L. So what's the structure here? How do we see this whole machinery? So first I have to tell you what is the rate vector field, but that's very simple because S5, as you might know, it admits a Hopf vibration over CP2. And in fact, the rate vector field is nothing but the flow along S1. Okay, so it's very simple. Then I have to tell you what are the rate chords. So yeah, with the usual one. Yes, of course. I think if you change it, you just change the direction of the Hopf vibration, right? If you rotate, you mean? Yeah. Yes.
But if you change, it can become along this three-way orbit, so it will kind of degenerate.
Yeah, we're going to perturb this. Yeah, it depends what you mean by change then. Yes, yeah, we're going to have to perturb. Yeah, I was going to.
You would like to have as little as possible.
Yeah, exactly. Yeah. Okay, you know about all the fine points. Great. Yes. Okay, yeah, so let me try and get through this example as quickly as possible. So we think of S5 as some S1 vibration over CP2, and CP2 itself, as you know, it has a structure of a T2 vibration over the two simplex. So this T2 is sometimes called the Clifford torus, just a name. But the point is that, in fact, our Legendrian lambda happens to be a threefold covering of the Clifford torus. So in other words, you can think of this lambda as just sitting over some point in the two simplex, just covering 3 times the Clifford torus. And what that means is the following. So you can now look at this Clifford torus in the way you would usually look at a torus. So this is T2 Clifford. We're sitting at a point over the simplex, looking at the Clifford torus. And over each point in this Clifford torus, there's still the Hopf fiber, right? So over each point here, we have the S1 from the Hopf vibration. And the fact that lambda is a threefold covering means that lambda will have some 3 sheets. There will be 3 points in this Hopf fiber. They fiber everywhere over T2, and these 3 points rotate so that we get some connected cover. Now, the whole kind of ingredient of the construction was the Rabe chords, which are the flow lines of the Rabe vector field. I told you the Rabe vector field goes along S1, so you'll see right away that there will be Rabe flow lines connecting these three sheets. And as Maxime just pointed out, this situation is very degenerate. We have these flow lines over the entire T2. Okay, so we're not gonna do much with that. So you have to perturb a little bit. This has been studied by some mathematicians a while ago. And it is known that after you perturb generically, what happens is that there's a single Rabe chord. Sorry, this is lambda now. Single Rabe chord with two endpoints, C plus and C minus, which looks like that. And so this single Rabe chord generates the space of classical vacuum. So remember, V was graded, so we have something in degree 1 that's given by the Rabe chord times C. And then we have some space in degree 0 that's generated by the empty Rabe chord times C. And then we can now compute the differential. So the differential from V1 to V0 should be some holomorphic curves that start at the Rabe chord C and they run to the empty Rabe chord. That means that they have no Rabe chord at the bottom. And it turns out that there's three of them. So the boundary of C, the differential of C, is the sum of three holomorphic curves, okay, which look like this. So there's going to be one of them here, here, and here. I'll call this P00, P01, and P10. So P00, P01, P10. And now to compute A, in this case, we have to choose a capping path. So we're going to choose some capping. And we can choose, for example, to cap with P00 inverse. So that means I'm going to take my capping path to be this, P00 inverse. And after I do that, I'll just draw it like this, P00 inverse, and so on. Then I get, as promised, three Wilson lines on my boundary torus. And these three Wilson lines, if you stare at the picture for a moment, what they look like is as follows. So we're going to have a trivial one when I concatenate P00 with the inverse. We're going to have something that I call P01 along the longitude and P10 along the meridian of lambda. Okay? So that means that our trivial cohomology element, A, which is the boundary of C capped with P00 inverse, is nothing but the collection of these three Wilson lines. And now I told you that to compute curve counts, you have to impose this equation. And as Alessandro pointed out, to really solve the equation, you have to choose some initial condition. And the statement is that, okay, so if you choose suitable initial condition, then the solution is unique. And it takes the following form. So it's a sum over partitions, product over boxes, Q to minus the content of box, divided Q to the hook length, minus Q to the minus hook length, times a Schur function with partition lambda. Okay. So this gives you the open string partition function for a stack of arbitrary number of branes on L, on the toric Lagrangian. Okay, so that's the baby example. Yes.
Is this A related to the quantum curves?
Yes. Ah, thanks. Yeah, that's a very good question. Yes, it is. There's a nice specialization of this. If you take n equal to 1, so just take one brane, then it goes exactly to that. So the Schur function collapses to something of a single variable, right? Just have one brane. So it collapses to 0 if the partition has length greater than 1, and it's just x1 to the n if the partition is just a symmetric partition with n boxes. In that case, this operator that I wrote here becomes just 1 minus y hat minus x hat, and that partition function becomes just a Qpokammer. So it becomes this very familiar kind of equation. That's for a single brane, but this is the answer for arbitrary number of branes.
So it's a generalization.
Yeah. Yeah, it's a generalization of quantum curves. But you can always write this thing in this language, in this Q difference equations. You can make everything explicit if you want to represent it in terms of functions. So you can still write this whole package using McDonald operators and so on. And in fact, there's even some refined version of this that Victor and Luca maybe not yet put out, but will put out soon. Yeah. Okay, good. Okay, so almost at the end of my time, but I still haven't told you what's the big deal with this thing. Well, why do we need it, and why do I keep saying that we need to pay attention to this data at infinity? So let me try to squeeze that into a couple of minutes. So the real issue with this is when you have multiple Lagrangians. Not multiple branes. We already deal with multiple branes on a single Lagrange. But when you have multiple Lagrangians, you're going to have at infinity some Legendrian torus, some other Legendrian torus, and then you not only have Rabe chords between them, but you also have, so on each of them, but you also have Rabe chords that go in between the two. Okay? So you're going to have some bigger structure for this Legendrian contact homology. So the kind of contributions to your vector space and your differential will depend very much on the relative position. So A will depend on the relative position of lambda I. And so curve counts will also change if you choose different configurations for the Legendrian torus at infinity. So in a nutshell, what really happens with the topological vertex is the following. In the topological vertex, the way it's usually discussed, well, people say that you start with C3, and you're going to take just 3 toric Lagrangians, Li, just exactly as before. But as I emphasized before, the issue is that Li, they all go to the same lambda at infinity, the same asymptotics. So the issue then is the situation is degenerate. You don't really have a well-defined curve count for this geometry. If you perturb, so the issue is you have these branes at infinity, they're exactly on top of each other, like that. And what I'm telling you is that if you now choose a perturbation of the branes at infinity in one way or in another way, you're going to get different curve counts. They're actually different. Okay, there's some curves that appear or disappear depending on how you push them off. So main results is first, what is the actual geometry of the vertex? And the claim is you have to use the so-called Rabe push-off. So I told you before that for a single brane, you had this Hopf vibration, and you had 3 sheets over the Clifford torus. And all you need to do if you want to get the vertex is you have to take the second brane shifted exactly along the Rabe direction and the third brane as well. This is not what they actually claimed in the original paper. But the result that they get corresponds to this geometry. And the way that one shows this is we actually computed the well, the cohomology, the Legendre contact homology. So it's a set of relations called A1, A2, and A3 at infinity. So this is going to give you a set of equations with many solutions. And one of these solutions, in fact, we prove is exactly the topological vertex. So there's a solution that corresponds to actually taking these three Lagrangians with this Ray-Plushoff, and then we find that the partition function is sum over lambda 1, lambda 2, lambda 3, C lambda 1, 2, 3, and then sure functions on the three branes. But then, as I emphasized at the beginning, once you have these relations, you don't just get curve counts, you get a bigger structure. So what you can do is you can look for other solutions. And in fact, you can do that. And there's three other phases, which are analytic continuations of the vertex to other large volume regions, corresponding to having two of the branes on the same leg or all three branes on the same leg. There's four large volume phases. And for each of these, you can find explicit solutions to these equations, and they tell you how the curve counts that come from the vertex, how they analytically continue through the singularity at the vertex into other large volume regimes. So yeah, I think I'm gonna stop here. Yeah.
What kind of formulas are for that other objects? Because the topological vertex is some matrix element between two diagrams that depends on the Archimedean diagram. What is the structure of this?
Of these other ones? Oh, yeah, that's a great question. Actually, it turns out they're much nicer and much simpler than the vertex itself. I don't remember the precise formula, which I should, because they're so simple. But I can tell you what they look like structurally. So, so basically, let's take, I don't know, actually, let's maybe take this one, where all three branes are on the same line. You're asking about these things, right? Yeah, okay. So let's take this thing. So I told you before that if you had a single brane, you would have this this thing that I wrote as sum over lambda, and then product over boxes, q minus the content over q to the hook length, q to the minus hook length, times s lambda. That would be for a single one, okay? So I'm going to call this the disk partition function. That for me counts multi-coverings of a holomorphic disk with boundary on that Lagrangian. So if you have three of them on the same thing, what actually happens is that you're going to have three disks, so one on each of them. Okay, so let's call this psi disk. And the partition function here will be something like psi disk on brane 1, tensor psi disk on brane 2, tensor psi disk on brane 3. And then in addition, you have some annuli that stretch between the branes. So you're going to have, for example, so what is the annulus partition function? It's even simpler than this one. If you have an annulus between two branes, 1 and 2, then let me define psi annulus for you as the sum over all partitions of S lambda tensor S lambda. So that would be an annulus. And there's some variants where you put lambda transpose and where you put some signs and so on. Like twisted annulus and anti-annulus, anti-twisted annulus. There's some variants of this. But the moral of the story is that the full partition function here will be the three disks and then some annuli. I think there's annulus like 1, 2, and there's going to be maybe annulus 2, 3, and maybe some annulus 1, 3. I don't remember the full details, but it's like that. And for all other phases, except for the vertex itself, you can actually write down a closed form expression just like that. So in terms of disks on each of the branes and annuli that go between them. There's a tricky bit that the annulus boundary actually links with some of the disks in a certain way, and so they create some bound states, but but the formula can be written down in a very simple way. The vertex is actually the most challenging one. We don't have such a nice presentation for the vertex itself. Yep.
So can you extend this picture to the refined vertex?
That's yeah. I would love to, but I hope some people will do. I think there's a very good chance. I mean, so for the unknot, I understand that it's in progress and almost done. So that would be the single brain, maybe in the conifold. For the Hopf-Link, I believe it should be very close, and then it's just one more step to the vertex. So
what would it correspond to in your picture this extra parameter?
I think we don't really know. There's a lot of speculation we can make, but we can talk about it afterwards. Yeah.
Yes, sir, and maybe I missed something. So you have some element of the skein module acting in super space, like on boundary of the Lagrangian, right?
Yes.
And you have specific element A.
Yeah.
But there are more elements in the skein, like in the skein of.
Yes. Yes.
So, like, would they actually correspond to something reasonable?
Yes. Yes. There is a whole description of the skein algebra. So okay. So let me step back. So whenever you have a three manifold, you have a skein module associated to that. As a Holmes-Lippertz skein module we're talking about. That's a little bit like the vector space of the Chern-Simons theorem, that three manifold with boundary. And whenever we talk about the boundary, we have a skein algebra that's a little bit like the skein module of the boundary times an interval. Okay, so that's like the algebra of observables of that Chern-Simons theorem. So in the case that we're working with, which is actually very simple, the three manifold is just a solid torus. So the boundary is a torus. And there's a whole kind of very well-developed description of the skein algebra of the torus. This has been worked out by Morton and collaborators. And so there's a description of that. I mean, I could write some explicit formula, but the upshot is that, yeah, I can give you some details. So the skein algebra of the torus can be expressed or generated in terms of some operators, Pij, that correspond to power sums along some Ij curves in T2, okay? And so basic example, so first of all, there's some statement that Pij, Pkl has some form. It's Pi plus k, j plus L times some factor here. That's like quantum number of the determinant of IJKL. Maybe inverse. So there's some algebra of these. And then they also tell you how these things act on the skein of the solid torus. So on the skein of S1 times D2, so there's a basis that's basically given by the Schur functions. And then the definition of this algebra is actually quite simple. So P01 on S lambda just adds a box. So it's mu is lambda plus a box as mu. Okay, so it's like box multiplication. Whereas P10, it's actually diagonalized. It's diagonal. So P10 S lambda is some eigenvalue. It's something like A minus A inverse over Q minus Q inverse. Minus Q minus Q inverse times A times the content polynomial of lambda in Q times S lambda. Okay, so this is then if you switch to a representation of the Schur functions as polynomials and variables, this is supposed to be some unrefined specialization of these McDonald operators. So everything is extremely explicit. You can compute.
Yeah, but you would have some special vector which you call Z open, right?
Yes.
So how do these operations happen in this particular vector?
Oh, Z open is going to be some linear combination of Schur functions. Yes. And this representation tells you how these things act. Does that make sense?
Yeah, there will be some formula, but there is no interpretation for this formula.
Oh yeah, there is an interpretation. So from the viewpoint, yeah, this is actually an important point. So you should think of these skein algebra as some Wilson lines at infinity. I mean, when we talk about A, so this equation here, you can think of it as an operator equation in Chern-Simons theory, where this is some operator on the boundary. So on the boundary, you're going to have some Wilson lines like 0, 0, 1, 0, and 0, 1. And Z is also some kind of, well, it's going to be some state of the Chern-Simons theory, but what it really means is that you take your solid torus and you fill it in with Wilson lines inside. The Wilson lines are the boundaries of the world sheets that you're counting, okay? And this equation tells you that if you use the algebra of Wilson lines in SUN Chern-Simons theory, arbitrary n, then the linear combination of these three Wilson lines at infinity, once you skein through the lines inside, vanishes. That's the interpretation. So it's a statement about the algebra of Wilson lines, but the Wilson lines inside are the boundaries of world sheets. So that's how you think about Z in this setting. Yep.
Okay, there are no more questions. Let's thank Pietro again.